Right, good morning, Year 10. Last term we finished by looking at momentum, and we got to this example here, which was working out the momentum of the gun and the momentum of the bullet was actually the same because the momentum is conserved after an explosion. So there was a question though that was left unanswered, which was when a gun recoils, why doesn't the shooter suffer a fatal injury? Because a bullet, we calculated, had a momentum of 5 kilograms meters per second, but then so did the gun. So therefore, the momentum cannot be what causes a fatal injury. Now, I'm going to have to give you the explanation for this in a few minutes, but today what we're going to look at is how changes in the rate of momentum actually cause damage. So the way we were going to look at this in class was we were actually going to use rugby pads, and I was going to get a couple of you to charge into this, but think about what happens with a rugby player as they charge into the rugby pad. Okay, what happens to both objects? So you've got a large object here and maybe a smaller object here. And think about the rugby pad. Before the rugby player tackled it, did it have any motion? The answer, of course, is no. Therefore, its momentum would have been 0. Does our rugby player have momentum? Well, yes, because he has mass and he's moving, so he'd have velocity. So what happens to both people when they collide and move off together? Right, now describe in terms of mass, momentum, and velocity as a single unit. Now actually, this section here in orange, I would actually like you to very quickly copy up. So very quickly, just pause the tape now and just copy that sentence in for me because we're going to explain that on the next slide. Okay, welcome back. So what happens when objects collide to their momentum is a little different to what happens to their explosion. So I've set up these two examples here, and I'd like to go through these with you. So say, for example, we've got a couple of people on roller skates. We've got the adult here, obviously has a larger mass and is moving, and we have the child here, smaller mass and is not moving. Now, if we do the standard thing, mass times velocity, we get the adult's momentum, and we get the same with the child. So 80 times 6 is 460, I believe. Okay, it's 480, sorry. So the adult's momentum is 480, mass times velocity. Okay, child's momentum is mass times velocity, which is 0. So their momentum is 0. Okay, now what happens is we combine their mass. So the adult comes along and scoops up the child. So what we do is we think of them now as one separate unit. Okay, both here and here. So let's put in a few numbers. Okay, so firstly, we know that her momentum is 480, but his momentum is going to be 0. So her momentum add his momentum still leaves us at 480. Okay, 480 kilograms meters per second, that's momentum. However, their mass, we now need to calculate as a single unit. So 80 plus 40 gives us 120 kilograms. Now, what we can do is we can work out the velocity after the collision. Okay, so we do 480 divided by 120. So you can put that into your calculators now. You can pause the tape and quickly do that if you want. The answer comes out as 4 meters per second. So basically, the adult and the child move off at a speed of 4 meters per second in this direction. However, we must remember to add a direction. Okay, because velocity is a vector quantity, she would be going, or they would be going off in this direction. So that would be positive, and if they were going that way, it would be negative. But because they're going this way, we're going to call that positive. That's forward. That way is forwards, and that way is backwards. Right, so what I would like you to try now is applying the same thing to this collision of cars. However, it's slightly different. This car is coming this way. This car is coming this way. They crash, they collide and move off together as one unit. So what speed would they move after the collision? Pause the video and work it out, please. Okay, so let's see how your basic arithmetic came up. So you've got mass times velocity. So 1,000 kilograms times 10 is obviously 10,000 kilograms meters per second. So this car has momentum 10,000 kilograms meters per second, but it's positive. It's going this way. This one, mass times velocity. So 1,000 times 5 is obviously 5,000, but it is negative. So negative 5,000 kilograms meters per second. Now they collide and move off together. Okay, so let's work out their total momentum first. So this has plus 10,000. This is minus 5,000. So plus 10,000 add minus 5,000 gives us a total of plus 5,000 kilograms meters per second. Okay, put that in there, that's the momentum. Now, their combined mass, because they're moving off as one single unit, is that mass at that mass. So that's quite straightforward as well. That is 2,000. So we've now got the momentum after the collision. We've got the mass of our object because we've combined it. So that divided by that should have given you, which means our crashed vehicles will move off at a small speed or velocity of 2.5 meters per second in this direction. Why in this direction? Well, this car initially had a bigger momentum, so that is why they would do that. So if you didn't get that, copy it down now, please. You can pause the video again, copy it down with this example and explain what is going on. Okay, so now that you've done that, I'd like you to have a go at the questions on the equation sheet. I'll give you about 10 minutes to do those. Make sure you show your workings and then I'll post up the answers in a few minutes. Right, welcome back. Now, this is another one of those delightful equations that you need to remember. So, firstly, you need to copy this down, make sure it's big and obvious. To calculate the force is worked out by the change in momentum divided by the time. Okay, and that can be expressed in the letters up here. Change in momentum divided by time gives you the force of the impact. So, where does each one go in the equation triangle? Let me quickly work that out now, please. It was, of course, this. Okay, so what this means is the force of the impact is calculated by how quickly the momentum changes. So there's your change in momentum. So every moving object has momentum, and the force of an impact is determined by how quickly that momentum changes. Okay, so let's just quickly go through an example. What do we need to consider when we work out momentum? Okay, well, momentum is mass times velocity. This you should remember from last lesson. Okay, so mass times velocity is momentum. So let's just very quickly go through an example. Any change, therefore, in the momentum will be due to the change in either the mass or the velocity of the car, or so any moving object, actually. So I've just used car as my example. So let's just say it's velocity. We would express it like this. So you've got the mass of an object multiplied by its change in velocity divided by the change in time gives you the force. So here's my example. Let's just say we have a 1,000 kilogram car. Okay, 1 ton car, 1,000 kilograms, moving at 20 meters per second. It collides with a wall and comes to a complete stop. So a stop would be 0, and that takes 0.2 seconds. What will be the force of the impact? Right, well, we could express it like this. Mass, 1,000, times the change in velocity. The car was going at 20. It's now come to a complete stop. So 20 minus 0 is 20. So it would be 1,000 times 20, which gives us obviously 20,000. Now, what we need to do then is put this into a calculation. So divided by the change in time, it took 0.2 seconds to stop. So put 20,000 divided by 0.2. And as we can see, if you've done this on your calculator at home, I'll just give you a quick moment to do that. Just pause the tape again. answer comes out at 100,000 newtons. Okay, so that is an incredibly large force. I mean, at those kind of forces, they pick you up with a sponge, unfortunately. But we can express this in a slightly different way. Okay, we could say, for example, say the mass times, do that separately, the initial velocity, the final velocity minus the initial velocity. Now, the final velocity was 0 because it had stopped. The initial velocity was 20 meters per second. So if we do 20 minus 0 divided by the 0.2, we get the same answer. Okay, they're just, again, these are the same equation, just expressed slightly differently. You can see there that the change in velocity is actually written out slightly longer. The change in velocity is the final velocity minus the initial velocity, so that's actually quite straightforward. Probably a good idea to quickly copy those out just as an example. Okay, so pause the video and do that now. So just to sum up, these are the ways that you can do it. You can show this. This is the example which is in your revision guide on page 71. Okay, force is mass times change in velocity divided by change in time. You could also express it like this: mass times in final velocity minus initial velocity divided by time. Or you could just say, because mass times velocity gives you momentum, you could just say change in momentum divided by change in time. In fact, you could even get rid of the whole change of part. So just get rid of that. Get rid of that. Even get rid of that. Momentum divided by time gives you force, because that would be simple. Your momentum has to be in kilograms meters per second. Time has to be in seconds. Force will be translated into newtons. So essentially, mass times change in velocity gives you the momentum, or mass times velocity gives you momentum, so change in momentum divided by time. Okay? These are all the same equation. Right. So, car safety features. Now, I've uploaded this diagram into files for you. The first thing I would like you to do is you can either print this off, or if you haven't got a printer, you might have to quickly copy it up. Okay, but what I would like you to do is try and identify how the various safety features actually work. Okay, so maybe just one brief sentence. How do the safety features of a car work? Pause the tape and just write one thing for each one. Okay, so time to actually now apply this equation. So let's just take the crumple zone of a car. A crumple zone in a car uses a simple physics principle to reduce the force of the impact. And it's the equation we've just been looking at. Change in momentum divided by time equals force. Now, let's just say a car is going along. It has a momentum of 30 kilograms meters per second. Okay? It slams into a wall and comes to a stop in 0.2 seconds. What is the force of the impact? Okay, so let's get our calculator out and we can actually work this out. It's quite straightforward. So we've got a momentum. Right, so let's change momentum. Now, it had a momentum of 30 kilograms meters per second, but obviously when it hit the wall and stopped, it went down to 0. So our change in momentum is 30. So let's put that in. 30 divided by, right, 0.2 seconds. Right, so in this case, we've got a force of 150 newtons. Okay, so we've got a force of 150 newtons of impact on this. Okay, now the crumple zone works by extending the crash time by a fraction of a second, but look what it does to the force of the impact. Okay, so what I'm going to do is I'm going to take the same car, but this time I'm going to just extend it by just 1/10 of a second to 0.3 seconds. Let's see what that does to the force. So, just clear that. Same momentum of the car, 30, but this time I'm going to divide it by 0.3. So we've extended the crash time by just 1/10 of a second. Okay, so not very much at all. But I've knocked a force sorry, I've knocked a third of the force of the impact. It was 150, now it's 100. What if I can extend it by 2/10 of a second? Okay, so now 30 kilograms meters per second divided by 0.4. Okay, 2/10 of a second. By adding 2/10 of a second to the crash, I've halved the force of the impact. And this is how pretty much all of these safety features are designed to work. Okay, they are designed to extend the time of the crash, because if you can stretch out this factor here, the force becomes less. So all of the car's safety features, pretty much every single one, is designed to extend the time of the crash just slightly to reduce the force of the impact. Okay, so crumple zones, seatbelts, airbags all work on the same principle to extend the crash time and reduce the force. Okay, so if you've got nothing else next to your diagram of the car, can you include that? Because that is really, really important. That is the main principle on how they work. Okay, final thing. So we didn't quite get around to answering this question last lesson. Okay, so how does a bullet actually kill you? So let's just say we've got these values. The mass of the gun is about 1.5 kilograms. The mass of a bullet, 5 grams or 0.005 kilograms. Velocity of the bullet, 1,000 meters a second. Now we already worked out that momentum was 5 kilograms meters per second, and the bullet and the gun will have the same momentum. So it's like an explosion. The gun recoils that way, the bullet flies off that way, but momentum after the explosion is the same. Okay, so they've both got, in this case, a momentum of 5. But it's not the momentum that actually does the damage of the bullet, it's its kinetic energy. Now, for those of you that can remember the kinetic energy equation, it's this, half mv squared. Now remember, the gun recoiled with a velocity of about 3 meters per second, but the bullet has a much higher velocity, 1,000 meters per second. If we put that into the kinetic energy equation, the amount of damage becomes clear. So half, 0.5, times its mass, granted quite small, 5 grams, 0.005 kilograms, but times its velocity squared, the amount of kinetic energy that you are struck with when the bullet hits you would be 2,500 joules. Okay, and you can go further with this. If you calculate the force of the impact over a very small area, say for example the tip of the bullet there, you can see how much pressure is on the target, because the pressure over a very small area means it will basically rip through anything. Okay, so that is how the bullet essentially does the damage. It's the kinetic energy of the bullet, not its momentum, that actually hurts you. Okay, so we've now looked at momentum and we've utilized the 2 equations. Okay, so there's 2 equations that you need to know. The first one is momentum is mass times velocity. And then the second one that you need to know is force is the change in momentum, which is mass times the change in velocity divided by time. Okay, right. The final task for you to do today is to get your revision workbooks out, so your white books with the blue stripes, and I would like you to have a go at the questions on page 69 and on page 70. Now what I will do is I'll upload the answers at the beginning of Wednesday's lesson for you, and we'll check them then. We are also now coming to the end of the topic of forces. So I'm going to do a bit of a revision lesson on Wednesday, and then next week I'm just going to set you a test covering as much of the topic of forces as I can reasonably find, okay, which would obviously take an hour in the lesson. So as always, I'll be online to help you during the lesson. Good luck, and yeah, that's it. So remember the questions on page 69 and on page 70 in your physics workbook, okay, but I'll put that up in just a moment. Good luck.